Welcome to the channel that ensures that you are able and empowered to perform your calculations, whether be it academic or for your business. Today we're going to be looking at the normal probability distribution. In the past or in the last two videos relating to probability distributions, we have looked at binomial probability distribution. The link is right down there. We have also looked at the Poisson probability distribution. You can also have a look at it. And then now we're moving into the normal probability distribution. So we're going to go over the following. In the previous videos, we looked at the probability distributions and we said the random variable is essentially a possible numerical value of an uncertain event. So we have looked at the discrete random variable, which was for your binomial and your Poisson probability distributions, and then we moved into the continuous. This is what we are now doing, the continuous random variable. So we need to understand what really is a continuous random variable. A continuous random variable is a variable that can assume any value on a continuum. That is to say, we can assume that there is an uncountable number of values. So in order to represent this, it becomes a little tricky to use like a bar chart that we did for your binomial and your Poisson, because we are looking for one particular thing. In the continuous probability distribution, the proper graph that we can put the probability distributions under would be what we call the normal curve. So we need to understand what a normal probability distribution is like. So we'll go through that. But for now, examples of what we call the continuous probability distributions would come from values such as the weight of an item in kgs. It could be 20, 30, 40, 15, 15.5, 15.5, 6, 7. See, we can measure it accurately. Time required to complete a task. One person is going to take 2 minutes, 4 minutes, 3 minutes, 3.5. Temperature of a solution, the height in meters. So you see, with the nature of the random variable that we're looking at, it can take potentially any value depending only on the ability to measure accurately. So we can drill down to the milliseconds if it were time. So let's understand the properties of a normal probability distribution for us to be able to have an understanding of what we're saying. So we're saying, number one, the curve is a bell-shaped curve, meaning to say that it is symmetrical about a central mean value, which is your mu. The tails of the curve never touch the x-axis, meaning that there is always a non-zero probability associated with every value in the problem domain. That is to say, it is asymptotic to the origin. The distribution is always described by two parameters. So they'll always give you a mean, which is the average, and the mean is going to be equated to what we call the population mean mu. So we're going to replace the mean, which is your x bar that we normally use in our samples, with the mu. And the standard deviations. Standard deviation, remember we did our calculations for standard deviation of group data and ungrouped data. If you're not sure on how to calculate standard deviation, please follow the links. The total area under the curve will always equal to 1. Remember the properties of probability. It is always equal to 1 or a 0 or in between, since it represents the total sample space. Because of symmetry, the area under the curve below the mu is 0.5, and above the mu is going to be another 0.5, meaning to say the 0.5 plus the 0.5 will give you a 1. The probability associated with a particular interval of x values is defined by the area under the normal curve. There's a formula that we can use to calculate, to figure out the z or to figure out the x, we can transform the z, the sigma, we can find the missing figure through like an equation. Because if you're given the z, you can calculate the sigma, you can calculate the x, or you can calculate the mu. So depending on what you'll be required to calculate, you should be able to do it. So the above formula is useful for finding z. Now, we're introducing z, and z is the number of standard deviations above or below the mean. So if it is above the mean, you're going to see it with a plus. If it's below the mean, you're going to see it with a negative. Z itself has what is called a standard normal distribution. So the mean would be equals to a 0 and the standard deviation equal to a 1. We can also try and put this under what we call the sampling distribution of the mean. So this one is going to adjust our data with the mean, and we're going to find the square root of n. So it is going to assume that if we have a distribution that is normal, if we just move one standard deviation above and below the mean, then this should cover about 68% of the observations. If we move 2 standard deviations above and below the mean, then we should cover about 95.5% of the data. If we move 3 standard deviations above the mean and also below the mean, then we should cover about 99.7% of the data. We're going to do a question so that you can practically understand what we're talking about when you talk about the normal probability distribution. So here goes the question. The manager of a local shopping mall has determined that the length of time patrons spend at the shopping mall is a normally distributed variable with a mean of 75 minutes and a standard deviation of 15 minutes. What proportion of patrons spend more than 2 hours at the shopping mall? What proportion of patrons spend less than 1 hour at the shopping mall? So this is a normal probability distribution question. Given our question, it is going to require us to draw what we call the normal probability distribution ourselves. Well, it might not be as symmetric as it was in the diagrams, but we'll try our best. So we're saying this is normal probability distribution, and we said the best thing that we can do, because the values can take any value, is to draw a curve. Forgive me, it might not be as you thought it should be or as you saw it being, but we're going to say this is our mean, our average. So our mean is mu, and our mu in this case goes to 75 minutes, and we're told that the sigma is equals to 15 minutes. So remember, we said for the normal probability distribution, we can either move up, so this would be 1 sigma, and then this would be sigma 2. So 1 sigma, 2 sigma, and this could be your 3 sigma. These are all positives going this side. Coming this side, it's going to be negative 1 sigma, negative 2 sigma, and negative 3 sigma. So if the data is normal, then it must at least fall within the 3 standard deviations. So we should now be able to do our calculations given that. Okay, so with the given data, just going to write it down by the corner like we always do. We say our sigma is equals to 15, our mu is equals to 75. What proportion of patrons spend more than 2 hours at the shopping mall? So we're going to say A. When they say more than 2 hours, Alright, more than 2 hours, we need to calculate the Z, and then the Z is going to give us our probabilities under the Z table. So we know the formula. The formula says Z is equals to x minus mu over sigma. Our x in this case is 2 hours. So 2 hours in terms of minutes would be 120 minutes. So I'm just going to put it here. 2 hours is equals to 120 minutes. Right? So we're going to say 120 minutes minus the mu is 75, and we're going to divide by the sigma. Our sigma is equals to 15. This is going to, in this case we have a Z of 3, so it means to say that we would have moved 1, 2, and we are by the sigma, which is plus 3 sigma here, and this is giving us a Z of a 3. So what it means to say that this is going to be the area between from here. If I shade the area, what it means, because it says more than 2 hours, so if I were to draw a small mini kind of diagram where this is our mu and then our sigma of a plus 3 is here, so they said more than 2. We're going to get more than 2 would be the area that is coming here. So we need to go to check for the area under the probability. We already know that this is 0.5, and a 0.5 would be somewhere here. So this is going to be a very small number, because by 3 here we should get about 0.4 something. So let's check the Z table and find out what a Z of 3 would equate to in terms of probabilities. Okay, so you should look at the table, and the table would say the standard normal distribution, and to find the probability of a Z of 3, you go to the first section or the first column, it says Z, and then that going to the rows, it would give you the probabilities. So the inside numbers are probabilities and the outside is the Z. So a Z of 3, it's exactly 3, so you go under Z of 3, and the first one is 0.4986. So we found that the Z of 3 is 0.49865. So this gives us the probability. So this is the probability of the area from the mu to the plus 3. So this whole area here is the one that gives 0.49865. And we already have a 0.5 this side. So what we want is the shaded area. So that is the area remaining after we take away this from the 0.5. Because remember, this is 0.5 and the other side altogether is 0.5. So we can simply say the 0.5 minus the 0.49865. That would give us a probability. So the probability of having shoppers who spend more than 2 hours would be a 0.00135, almost a 0. It's almost a 0. This is almost like there's no one who's going to spend 2 hours, because if you look at it from an accounting or a mathematical perspective, it does make sense. No one is going to spend more than 2 hours, because your shoppers are spending 75 minutes. 75 minutes is like an hour and 15 minutes. So who's going to spend 120 minutes? The shoppers would all be gone. Most probably about 0% of the shoppers, because this is the average, and we're saying it follows a normal probability distribution. So if it follows a normal probability distribution, then we're just subtracting your 15 from this. Now, looking at the other question, it says, what proportion of the patrons spend less than an hour? So effectively draw your diagram. That's the leading point or the starting point. So, sorry, it might not look like a normal distribution. So we're going to say our mu is equals to 75, and we know that our standard deviation is equals to 15. So the question is asking, what proportion of people would spend less than an hour? Where is the hour? Is the hour this side or that side? Remember, this is an average of 75 minutes. So 60 minutes is somewhere this side. So you're going to see that when we even calculate, our z is going to be negative. So put in your z formula. Z is equals to x minus mu over the sigma. This is equals to, what is our x? We're looking at less than an hour. If it says less than an hour, then we want to say whatever the z is, it must be coming this way, that is less than. So this is going to be a 60 minus a 75 divided by a 15. So this is a minus 15 divided by a minus 15, which is a minus 1. This is a z of a minus 1. So the z of a minus 1 is like moving 1 sigma this side. So the probabilities, what it would do is to give you a calculation of the area from the mean mu to that 1. So we do have the probability. When we check under the tree or under the table, we're going to get the probability of this shaded area. But the question says less than. So remember, less than, we are looking for this portion here. This is what we are interested in. We already know that this is 0.5. We can somewhat estimate that this is going to be about 34 or 35%. And then what remains here would be a smaller proportion, roughly about 16, 17, 18 or less percent. Let's do that. Let's check in our table. So looking at our z table, and we're looking for a z of 1. So you would go under the z, and the area inside would give you the probability. This is a 1 point nothing. So we just go to where it says 1, and we look under the 0.00, that first column, and that gives you a 0.3413. Here. So we've got a 0.313, writing it down. So the probability of that corresponds to a z of a minus 1. The minus 1 is just giving you the direction. You won't find a minus 1. What you're just looking for is the z of a 1. So the z of a 1 here is 0.3413. So that's about 34.13%. So this is 34.13%, and this is 50%. If I just write it in decimals, then this is 0.3413. So you got from here to here 0.3. They said less, so we are interested in this area here, less than an hour. So what we can do is to say, we know that this is 0.5, take away the 0.3413. So we can simply say, therefore the probability is 0.5 minus 0.3413, which is equals to 0.1587. Meaning to say that the probability of finding shoppers who spend less than 1 hour is 15.87%. One could have said 0.5 plus 0.3413, which gives you about 0.8 413, take away from 1, because you're looking at the whole area, it will still give you your 15.87%. So that's how you work out the normal probability distribution using the normal Z formula. So you can either be asked to calculate for areas in between, or areas that are less than, areas that are more than. What you need essentially to be able to do is to draw, if you draw the diagram, right, and you know that this is your mu. So if you're asked to calculate an area that is, say, where your mu is here, and then they say 1.5 sigma, 1.5 z, a z of 1.5 and a z of 1.7. This is negative, this is positive. So what you would do is to look for a z of 1.5. It will give you the area from here to there, this 1.5. So that's the area that you would have, and then the probability of the area from here to 1.7 would be this one. So if you're looking for this whole entire area, then it should be about 68, 69, 70%. Then that's the balance that remains. So just be able to add, subtract, easier when you draw the diagram. For some calculations, this topic is skipped for just the purposes of assessment, but it is useful when you come to the hypothesis testing, because it is based on the normal probability distribution. So the understanding of the normal probability distribution becomes key or important to this. Thanks for watching.